Today we're pleased to introduce Joe Judge from the Mitre Corporation. Joe has a distinguished career in information security, particularly network security, dating all the way back to Bell Labs and several incarnations in between. He's been most recently at the Mitre for 5 years. I know he's done some work in looking at forward deployed systems and how to protect network security in those. But today he's going to be talking to us about software assurance.
Thanks. So I'll take a few minutes and maybe I'll cover the what Mitre is first, so it gives you an idea of where I'm coming from. So Mitre is a federally funded research and development center. It's not like a normal company, but it kind of is. So Mitre is a company that is focused on working in the public's best interest. We're not a defense contractor. We work with sponsors that typically would be worked with by defense contractors, so the Air Force, the DoD in general, NSA, FBI, Department of Homeland Security. And each center that we have at Mitre focuses on a different space. I work in the DoD center. So a lot of my work is with the Air Force and DoD acquisitions. And I'm sorry, but software assurance sounds like the most boring topic, and acquisitions to most people sounds like a very boring activity. But for my part of the Air Force that I work with, they procure systems. Again, I'm sorry it sounds boring. What the military has a huge set of folks who are at the pointy end of the stick. There's another set of folks on the backside who help logistically supply them. And that could be from hot coffee to systems, applications, software. And if I can explain to you kind of how my job is affected by software assurance and what's going on in industry, you can probably Google around right now and find really good topics on software assurance that come from Booz Allen Hamilton or from the Mitre Corporation, and they will give you a good sort of basic set of information of what's going on, what you should do, frameworks for approach, tools that you can use. But it might help, I'm hoping, if you get a sort of practitioner's view on it and see how we actually put these things together and why they're important. So I'm going to assume most of you know the basics about software development, and I'm not going to belabor too many points early on to impress upon you how much it's important, but I'll start with the basics. Everything's connected. I know people say that, but I come from a time where I remember the first internet toaster, 1991, the Interrupt conference, and the second year when they actually add a robotic arm to hook up the toaster to make the bread go in the slot. This was clever stuff back then. Today, everything's connected. A toaster is not unique on the internet anymore. Webcams are not as interesting as they would have been before. Remember when the first Encyclopedia Britannica came online, or the Vatican. And these were shocking developments in the early 90s. And what we're connecting now is complex. So we're connecting things behind infrastructures and protections that are also very complex. This is an example of an IBM store, the systems that make a store that you go to, that IBM has control that sells systems and computers. This is their block diagram of the systems infrastructure. That's just a store. So the important thing to me to note is I keep thinking of the internet, I had been, as this thing that's built up of pieces. As engineers, as developers and engineers, we view things as atomic components that you put together, an ISO stack with applications at the top and hardware way down at the bottom, and that we picture an interconnectivity, an internet, a cyber, whatever you want to call it, the matrix, as an expression or outcome of this thing that occurred. But okay, that's true, but flip it upside down. Right now, the internet or the cyber infrastructure connects, underpins everything now. You have a piece of equipment that measure temperature on oil pipeways connected over the internet. You scan enough, you'll find one. There are lots of neat pieces connected to the internet, and these now connect things you wouldn't have thought connected before. So these pieces that we connect, Google today, you hear stories about the United States power infrastructure and Chinese hackers and the GhostNet and people are breaking into the power infrastructure. There's one example of sets of computers that control our power, our electrical power infrastructure, may or may not have weaknesses because eventually, at one way or another, they're connected to the internet. These things are built by people who write software and stick it on pieces of hardware. So this is an example of a software flaw. It's a dumb mistake. I have a floating point integer that's held in a very large sort of 64-bit bucket, and I shove it into a 16-bit integer bucket that's signed. You have to watch out, right? I mean, at some point, you're taking a large number, shoving it into a smaller bucket, and the top bit's set, so now it's flipped negative. And if I took 65,536 and shoved it into a long int, signed int, does it make it -1? Or is it 65,536? Signed and unsigned becomes important. All these things become important as software developers. You're supposed to know this stuff. A lot of languages will cast things for you, but how it actually cast it, what was it that happened? And especially for test cases, are you testing that the kind of data that we shove in here is within a certain range so that it doesn't overflow, or are we testing for overflow? But I see it from a different point of view because I've made these mistakes, and they're easy to find, and there's tools available there. But these flaws that we put in, I don't know if it was an accident. This flaw, for example, this exact source code was part of the Ariane rocket. The French, out of French Guiana, they set this rocket off after a decade of work and about $7 billion of programming and time and building and engineering and loading it up with $500 million worth of cargo, and it flew for about 40 seconds. They had a problem with that 64-bit number being shoved into too small of a bucket, and it made a mistake. It didn't cost any lives in this one, but we have examples. The Patriot missile, in the first Gulf War, we had Patriot missiles that would shoot down Scud missiles, incoming Scud missiles, and we had a problem where we round numbers a little bit off. And so it would just miss the Scud, and the Scud would hit and kill people. So my point is, go back a slide, software flaws can have real-world impact, not just financial, but we have software everywhere now. All right. Now, from my point of view, when we're acquiring software, you guys are building software for me. I do care whether it was intentional or whether it was accidental, but at some point, the exercise of that weakness may be intentional, maybe accidental. With the Ariane rocket, it was probably an accident, and actually, the feedback loop to test that variable was too slow, and the rocket was moving too fast. So their correction would start a wobble. And it was an accident. Everything seems to point to an accident. But at some point, the expression of that outcome doesn't matter whether it was an intentionally added flaw because one rogue developer was all pissed off, or whether it was an accident, it was a coding error, that just a mistake, they forgot it in their test case to check those things. It doesn't matter because the actual expression of that and the impact doesn't care. A bad guy trying to hack your system doesn't care how that flaw got there, unless he put it there. He doesn't care how it got there. They're exploitable. They're weaknesses. They exist. I'll try for them. And they're pretty well-known ones, buffer overflows and integer overflows like that. So even blindly, without even knowing the source code, I could test for the most obvious thing, SQL injection, when you take input form from a web page. The traditional mindset for most of the people who work in information security, information assurance, has been focused on, again, that ISO stack at the lower pieces. Firewalls in the 90s, firewalls and network security, and inspection of content flows, and system security, and making sure you lock down your system and put firewalls up, or you have host-based firewalls. Maybe put tripwire in your system and look for integrity checks in case something changes unexpectedly on your file system. But if you put all these things in place, and you open a hole through your firewall so people can talk to your application web server, and you reach past the system security and let them reach inside and touch your data or your application logic that you wrote, then they don't really help. Those are just little holes in a fence that someone can reach through. It's about the data. There have been cases in the past, well, I've been doing this 20 years, but bad guys break into a system. Oh, it's the system that financial services has all this money that they move and bank account data. And the guys break into the system. They use that as a hopping point for somewhere else because they didn't know what they broke into. They just were looking for system access to anonymize their connection somewhere else. They could have been rich, but they didn't know. Times have changed. It's about the data. It's about the data that makes a difference. So I say weaknesses and I say vulnerabilities. But Weakness is something that may or may not cause a potential to be a risk that actually affects, that actually becomes evident. Vulnerability, and this is, I'll take these words from like Bob Martin, or someone who's worked in the assurance space for common weakness enumeration and pieces like that, and then I'll tell you my spin on it. So vulnerability is actually something you have to deal with because it will express itself. A weakness to him is a potential. It may or may not be an actual vulnerability in your code that may be exercised. And those are true. If I look at a piece of code and I find that you have a little buffer overflow somewhere and it's overflowing a buffer that's on the heap and stuff next to it doesn't matter, then I don't really care, because it won't really hurt you. But that's a weakness to them. But something that actually might be a stack smash that might actually evince control, that you can actually jump around in memory and execute other code, well, that might be more of a vulnerability to them. I take it a step further. One of the ways that we measure in the space I work is there are vulnerabilities. There are these pieces that you enumerate up. But at some point, you have to make some judgment on whether that's actually going to affect the mission of what you do. And that's a risk. So weaknesses, vulnerabilities, and risks. Risk is something that actually you factor in the other pieces. For example, I may have protections somewhere else that prevent the exercise of that exploit, like a proxy server that's filtering long input statements, and I have a buffer overflow. Well, that buffer overflow, as long as the proxy server is working, I'm protected. So maybe together, as a holistic sort of point of view, it's not a big risk. I can mitigate this another way. All right, I sort of hinted about the threats, but spend more time on this. Early part was about how this is all linked together. Okay. I remember the first internet worm. That was the first big event. And it was so unsophisticated, and the tools to do such things were not really available. You had to be really good, and you had to know your target systems real well, and you had to really understand and have access to source code. In the late 80s, I was working at Bell Labs, and well, of course we had the source code. We invented Unix. And we had that available. It makes you a better programmer to see examples. What you have today is what I had with the people that I work with. But everyone has access to source code today. There's open source projects that are great examples of how to build things. Application web servers, native pieces that talk over the network wire, things that send UDP packets or TCP packets, or how to craft tunneling over ICMP to get past a firewall. Great examples out there. The tools purpose-built to attack and cause harm to systems, well, those have grown in sophistication also. So the more that the top pyramid of the people who are really clever build tools that show or example how to do some of these things, well, the more people who aren't as skilled can use those tools. So it's a raising of the bar. It's the normal way that things happen. You build upon things that build upon things, and you can get farther because of the stuff you leverage. So the sophistication of the attack today is different. And remember when I told you that there's people that have broken into financial systems and they were sitting right next to banking statements or financial information, and they didn't know it. Well, the people who actually want to leverage that sort of thing have been paying attention also for the last decade, and they know it. And over time, the attacks are getting more serious. And you might not see these in your average run-of-the-mill sort of company, but for critical infrastructure, financial services, things that make a difference, these tend to see more sophisticated attacks over time. Attacks you might not see. Malware that gets right past the signature, the antivirus signatures that you have because, well, it's just signature-based, and it's a list of signatures. If we sat down today and took half an hour, literally half an hour, to write a little piece of malware that delivers itself over email, none of the antivirus of the people that you send it to will ever trigger. It's the wrong signature. So our threats are getting pretty sophisticated over time. But where I work, again, it's real simple, right? I have suppliers who make software for me. And these are defense contractors. And on the government side, we say, hey, we'd like you to build this. And please build that. And we try to make sure, as best as possible, we specify what it is you're building. We try to talk to you about, we need to do this, we need to be this fast, process this many messages per second. And a lot of our stuff is very much measurable. Radio frequencies or bandwidth or processing frames per second for video. It could be any one of these things. And we try to specify as best we can that when you build software, it needs to be this secure. And we try to make sure we can point to measurables that we can actually check during the course of running this. But the reality of this relationship is very different than most of the folks. I mean, we know it where I work, but it's really kind of deeper than we thought. Nobody writes every line of code anymore. It makes no sense. So if I were going to write a piece of code that processes images, well, there's lots of image processing libraries out there. And some of them are available freely in open source. Some of them are commercial libraries. Some of them are various licenses that are free within quotes or free with actually as in beer. Could be shareware, could be privately run little groups of people that just do their own code chunk and library, make it available in Google Code, or it could be a group of people that actually collaborate, because there are all different kinds of projects out there. And it makes sense to leverage such things. You might build it yourself, but even when you build it yourself, you leverage some kind of libraries. So no code today is ever really sort of done in a vacuum and in a clean room. And I'm sure for some programs, from some special applications needs, they probably do that. Everything from scratch, work in a clean room, all that stuff. But for most of the things we do, we collect and aggregate, we integrate, we build glue code and stitch pieces together. Because a lot of times we're facing the same things you guys are. We have time, cost, and schedule to hit. And my Java media framework's not working, and I think I'm just going to scrap it real fast because I have to hit a deadline, and I'm going to go get this piece of assembly code that does the screenshot, and I'm going to collect the things in a directory and just SCP them over or rsync them. Because you know what? It's got to work. That's a kludge. That's a hack, but it works. So you make design decisions. You make shortcuts. You do what you can to meet the need. And if it doesn't matter, but what I do matter is about affecting that supply chain so that when they do design decisions like that, where they do make implementation choices, that they try to make good decisions about it, so it's not done in a way where it's maybe more insecure. Because honestly, you could do it this way or that way. Actually, I have a problem that can be solved that many ways. Actually, I really want you to figure out how to solve it. I just want to set the goal, and I want the designer and the developers and the engineers to help solve how to get there. I don't want to overly burden them with exactly this is the path I want. Well, then write the code yourself. So we work very hard on telling them what we want them to produce, not how to produce it. But in some cases, when it comes to software, we do want to specify a few things. All right. I'll keep beating this dead horse about threats. So if you buy my story, and you don't, a lot of security is viewed as hand-waving, and maybe we're, Chicken Little. This guy's really not falling, and come on, how likely is something like that to happen? There's a book called Blind Man's Bluff. It's awesome. It's about submarines and submarine warfare in the 1970s. And there's a story in there. And in that story, they talk about the new class of nuclear subs that came out. We had them first. And we were quiet. Perfectly quiet. They couldn't track us. The game of submarine warfare was sonar and listening, and you'd hear them and hear whoosh, 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 just like the old World War II movies. And you'd hear the whoosh, whoosh, whoosh of the blades as they're pushing their little diesel engines through the air. And as soon as you go nuclear, quiet, no engine noise. But what you get is propeller noise, maybe. Depends how you design your propellers, and we were really good at it. We had subs that no one can follow, which meant we could sneak behind them and follow anyone else. We were awesome at it until they came out with nuclear subs. And they had the same things we had. And then in that story, at one point, there seemed to have been this design flaw that somehow creeped into the Russian submarines, where they procured certain chips, and when they was the motor controllers, and one of the props was slightly different in rotation than the other one, just enough that you can hear when they turned and when the body eclipsed the other one. Now we can follow them. They're moving, they're turning left, they're turning right, they're going straight. The game whole changed because of one mistake on one chip in one little chunk of code in a BIOS of a little chip that controlled the motor. You can read other stories too. There's a bunch of other neat stories like this. If you like the kind of spy versus spy kind of games from the Cold War, At the Abyss is another story with examples of how we played games against each other. Well, if that's what we were doing in the 1970s, imagine how much time has progressed and how better we've gotten or they've gotten and how the competition has happened in normal Darwinian evolution. It's going to be interesting stuff now. But again, like them, we also procure, everyone includes open source, cuts off the shelf, commercial off the shelf software. Why build something from scratch if I could just license it from this company that makes something pretty cool? And it might be a darn good idea. It saves cost, schedule, time, and it's probably, and if as long as it works, right, why not? GOTS. There are pieces of stuff that we take that only we have access to in the government. So maybe certain firewalls or certain IDSs or something like that, intrusion detection systems that we may want to use, which is our own. It's not really publicly known. It's obscured then, so maybe we have an edge there. And again, free and open source. Nobody writes code or builds systems without borrowing, and stealing from other places. An interesting side note, though, is I read a neat report about software reuse. This is not software reuse, right? This is someone purposely built a library to do JPEG compression with wavelet JPEG 2000 or something. And there's like 3 places on the internet that have that available. Yeah, that's a library. It was meant to do JPEG compression and decompression. There might be another piece of code, which is a whole application, which has pieces on that I'd love to have. But it turns out no one really does software reuse. They don't steal code from each other, because it's more work to craft someone else's code into your needs than it is just to write it from scratch yourself. But the libraries are what I'm talking about, whole cloth libraries that do an atomic function that you really want to leverage. And I know this sounds odd, but these have a provenance. So that program, Joe Judge worked on, and Bob Martin, and these people, and that's the core development set. And for every change they made, they check it in. It's over Subversion or CVS or something like that, so it's all attributed. We use authentication, so at least we know the people that are checking in code, because it's our little code project. We don't want people checking in random dumb changes. We're not Wikipedia. But that's not true all the time. And sometimes we do use code where maybe it comes from unvetted creators. That makes me nervous. And our current processes do allow that accidents can happen. Like I showed you the picture before in acquisition, there's a large surface area that's exposed. All right. So I'll tell you the folks we work with, how they think of it. They think this is important. The folks I work with, they get it. And they understand. And they do understand that there are motivators behind some of these folks. Any of the stuff I give, any of the stuff that I share with you about these folks is public knowledge. You can Google for these things, and I usually put the source at the bottom if you want to Google for it. There are neat and interesting things if you care about the sort of software threats and kind of what folks are doing about it. And I'll just take my summary for today, and you can pursue it on your own. So, National Security System, NSS weapons. We have neat things, and again, you can Google for this. I'm not oversharing. Everything's on a network these days, and most of the time the network is starting more and more to become IP. We still have odd, goofy networks that you probably don't have access to, and they go over radios, and they're all very strange, and they're synchronous networks with little time slots and odd things. And the kinds of things you see in the normal world, you see in our space. Vulnerabilities, and of course, being network connected. Systems that are network connected means remotely you can poke and prod at them and test them and manipulate them. There are some interesting quotes that went with this one. There was a public slide presentation. There's a 554th wing gave about software assurance. 554th does, for the Air Force, lockdown desktops and software assurance, and they provide tools, and they really get this thing. And their presentation, you can go for it, it was Major Weber. They said, what if? What if I can modify the readiness of an Air Force unit? Ready, not ready, deployed, not deployed, busy? What if I can change? Air tasking orders is, if you think of a concert, any Air Force mission is a concert with lots of moving pieces. And way ahead of time, they coordinate what the music looks like. The tempo, the beat, the rhythm, and when's everyone doing something. Think about it. I mean, we have planes that'll go 20 miles and run out of gas because they're burning real hard. So 20 miles, I'll have a tanker up and ready, then they can refuel and come back. And you have all these moving pieces, and there might be thousands of these actors playing around in the big theater. And what if someone can alter the pieces of that? That would be bad. What about financial information? Just modify, if you can break into the system that deals with, maybe paying our airmen and modify their financial information. A guy worrying about his finance because he didn't get paid for 2 months in a row is probably not focused on his job. What if I could change the status of the munitions? Oh, that one's already shot. Don't worry, you're out of ammo now. That'd be perfect. Or in my space, more on the acquisition side, what if we put out acquisition documents? You can go to any website, this is public knowledge. Here are the things we're asking for an RFP, and the defense contractors post back. It's a very public process, very transparent. Here's what we're asking you to build. And anything that's really secret, they moved into that place. But for the unclassed stuff, here's what we want to build, here's what kind of airplane, here's what we want it to do, and we solicit your proposals. And well, what if someone changed that? Changed it after, changed it before. So data integrity, all these things, these guys get, and they get what it could be. Now, I keep talking about software development, but also notice I keep talking about things that are not software, which are really supply chain things. But when I think about software development, I'm like you. I'm used to writing code. The actual maybe deployment of it, I'm done. Here you go. To places that actually move lots of pieces of code and they update and upgrade infrastructure. Think about Microsoft updates being pushed out. That process better be secure in and of itself. Or you can have the best, most secure piece of software, but if it's not tamper-proof when you're delivering it and someone accidentally mucks with it or on purpose mucks with it in delivery, you've got a problem. So you think about the kind of effort they had to do to secure that. This stuff could kill us if we get it wrong. If you run a piece of software on a wildly insecure system, hey, everybody, here's the root password, just log right in. And we'll just share that account so we won't know who did it. Then that's a problem, because no matter how good my software is, if you can modify its configuration or modify its variables in memory or modify the binary, then I don't have much of a chance. So I worry about all these pieces as well as sustainment, because once we're done, it's not fire and forget. We put things out to the field to do a purpose. And of course, we deploy today on Windows XP Service Pack 3, but that thing might be in the field 10 years. What's the upgrade path? How do we maintain currency? Or if a new CVE came out for that one application that you integrated in, what are you going to do about it? You need to make sure you have that as part of your planning when you're building your thing. There's a life to these things. There's a life cycle to these things. So there we go. When you put these things and make them clear to people, they start thinking differently than when they make design choices for software, how they develop. Because what you make early on, what you think about, impacts how you might have to take care of it. So those are the pieces that worry us. We've got a lot of moving pieces, right? We worry very much about the deployment piece. We worry much about sustainment. We worry about building. We have worries all over, 360 degrees. But the good thing, I'll say good things now, not threatening, scary things. Good things are, what to do about software assurance is not rocket science right now. We still have things to solve that are tough, but there are some things to do. Even at the highest level, if you can do a repeated set of systematic activities to make sure you increase the trustworthiness, the reliability, the resilience, a predictable execution, the ability. Now, depending on what organization, right? If you read any NASA document, they worry about safety, and safety is their trigger for software assurance, because they worry very much about a rocket doing the right thing and not publicly, visibly blowing up and hurting people. And that's a driver for them. And in other places, you'll find there's a different motivator. And often in security, you hear people talk about confidentiality, integrity, availability. Well, in some places, one of them is more important than the other. Doesn't mean the other ones are unimportant. But if you worked at a place like financial services, my example from before, integrity is real important. When I write down that person has, or I compute somehow that person has $5,123,000 in their account, that number better not change. It better not get bigger or smaller, because that's a bad thing. I have an SEC worried about me, and I have people that would complain if the money disappears, and I have people surprised if the money increased unexpectedly. So they do care about disclosure, but it's a quick race, and integrity might be slightly more important in some cases. Well, I work in a place where maybe confidentiality is more important right now. What we have and what we know, how something's built, is much more of a threat or a concern than maybe numbers in a bank account or something like that. So you'll see from different organizations that the thrust is differently. The folks, I guess the first one's the National Security Systems. The Committee on National Security Systems is a good one. That's why I sort of made it bigger. But you'll see a theme here. So I keep talking about software assurance, but let me tell you how I see it. It's good behavior under an umbrella that stitches together other disciplines. We'll take information assurance. I'm really an information security guy that just happens to have spent a life being a developer. It's not true for all information security people. So they have very much controls and rules they need to worry about. We have a list of controls called IA controls. The 8500.2, it actually, first half is boring reading, but there are a bunch of technical pieces in there. For example, if you're going to build a system and you're going to manage users, how you should store user account information and passwords, how do you manage them, how do you get them to show up, how do you get them to leave the account system, how are they triggered by a person leaving the role or responsibility, and what do I do about knowing the state of that person while they're under management? Like, has he logged in 30 days? Maybe I should idle out his password until he comes up and asks for it again. He hasn't touched it 90 days, maybe he needs to be locked out. So there are rules like that. Well, wait a minute. If you guys are building systems that I'm the security guy for, wouldn't it be incumbent upon me to maybe tell you about that rule? So when you are designing it, you can make design decisions. Derived requirements from the IA controls that say, well, you know what, we were thinking about plopping this Java application on top of a Windows box. Why don't we just leverage the controls and the user accounts from within Windows and just make it a normal application, as opposed to making it like a kiosk mode where you log into our application, because then we don't have all this extra work to do. Perfect design decision. In some cases, maybe in other cases you have to do something different. So there's an example where software assurance, it might be best met by maybe systems engineering people and information assurance people talking to someone who actually writes code on the program, so together they make good design decisions. What we see a lot is this separation of roles, where information security people are worried about firewalls and intrusion detection systems and antivirus and technical controls. All right, I have a graphic that moves this way. I said it before, but not really importantly, but it all really comes down to predictable execution. I want my programs to do what they're expected to do, what the user asked for it to do, and users with requirements are not always clear, and they don't ask for all the things they want, or maybe they do, but it's not really the stuff they need. If you are the person making design decisions and implementation decisions, and writing code is an activity that is actual design at the point you're actually making the code, there's no one who's going to tell you a requirement so clear that you're just cutting code like a code monkey. When you're writing code, you're interpreting a requirement typically, and you're making good decisions based on what the language offers you or choices. You may not have the choice of what language to apply, maybe you do have a vote in that stuff, but when it comes to writing code, you're making design decisions. So it's about predictable execution. It's about the code doing what it should, regardless of whether or not the customer specifically said, well, I want it to process these kind of messages. Oh, I forgot to tell you, when it gets any message that isn't like those, please reject them. That almost smells like common sense. It's a robustness issue, an availability issue that a designer or a coder would probably code it the right way, but that always doesn't happen. So what we're focusing on now too, I notice, like I said before, that we often look at, they give requirements, we interact with the user, we build them, we look at policy, and we do what we need to do, and we test for what we need to test for, and we have those hurdles we have to hop over to get it out the door, either a deadline or a user acceptance or something like that. Commercial industry has the same thing. But like I said, there should be a set of things too that you should bring to the table saying, and here's how it should act when things are bad. So the use of lots of stuff available out there today, runtime analysis and fuzzers and things that actually distress your application, perfect stuff. Here's an example. Back when I went to school, there were dinosaurs roaming the ground, but my department head allowed me to do a small project on the side. I just was shy a couple credits to graduate. And he goes, okay, so, pitch something. And I pitched a little robot tethered to an Apple II, 1981. And that's what we built. And worked all the pieces, ready to present my end of quarter. And the first thing he did was ignore everything I said and start pounding on the keyboard. I almost freaked out. He's just pounding on the keyboard trying to make it do something wrong. That's exactly the kind of testing we should be doing sometimes. It is not what people expect. It's easy to test what we want. Here's a summary slide. Again, I'm just going to rehash all the same stuff. There are things we can do. There's a lot of big words here too. Threat modeling and analysis and requirements engineering and fail-safe. There are a lot of software engineering and software quality engineering stuff you'll probably learn. Now, moving forward, I'd like to tell you a little bit more about kind of what I'm doing and how we're applying some of these things and why they're important. Okay, I call it current progress, but it's really how things are happening today. Okay, I think you guys get it. There's a problem here. Software could be coded accidentally wrong. It could be on purpose wrong. And Lord knows we take these things and put them at places where it's exposed to risk. Everybody does. The Internet's a great risk laboratory, a threat laboratory where I deploy software, see what people do to it. This is a software assurance problem, but it's part of a mission assurance problem in a general overall umbrella. And again, mission assurance, again, is a set of activities that integrate these pieces, not just for the purpose of software, but for the rest of the pieces too. There are significant risks across the life cycle. And we're working within, you guys have probably never heard this stuff. So everyone has a life cycle. We have one too. It's called the DoD 5000. And it's a set of phases where you decide and select and you build and implement and you deploy and run. You can pick any life cycle. It has phases. And there are lots of people trying to break this down into something that you have these phased set of developments where you're making sure your requirements are right before you cut code. You're implementing in a way that makes sense, and then you limited test it. And then you deploy it in a limited way, then open up to greater deployment. It's a staged set of things to do. But in our world, we also have this thing called DIACAP, and it has a subset of stuff we do for the Air Force called CISU. And it is exactly the security pieces specifically. Well, I forget the engineering part. There's a lot of parts there, but just focus on the security pieces for a second. Answer these questions. And that's what I spend my time in that space. And it's activities spread across the life cycle of that design and develop and deploy phase. Every day that we work, we make a case. We're like lawyers. We defend what these guys built on my program. If you guys are my developers, my job for like the IA person for your group, the information assurance person on your program, my job would be to make a case and defend why what we built is allowed to connect to the Air Force networks. That's my job. My job is to be working with you all along, so when I make that case, it withstands scrutiny, but in the end, near the end of the different phases, I'm defending a case, either through the design phase that you designed it right and here's why, or why we built it right and here's why. And that includes test data and methodologies or any kind of documentation that I can show that shows what we're doing. But what I don't have is actual arguments to make a case like a lawyer. Well, actually it is more like a lawyer. It's a subjective set of phrases with a guy waving his hands saying this is good because of these reasons. And as long as it's a reasoned argument and it fits within like what smells right, it has a good chance of going forward. But it hasn't proven anything. The guy at the other end, the reviewer, the auditor at the other end, that says yes or no, I haven't given him something definitive to put his teeth around. So for those weaknesses that are listed, well, there's no listing of weaknesses, but if there was, then the paths to get to those weaknesses in your code, oh, I'm sorry, there's no way to measure those paths. If we had something like that, I can prove for the known weaknesses to things like this exposed to that kind of threat, and these pathways to get to it are impossible because I did these things and there's a measurable way of doing it. I don't have that available right now. And of course, even in our space, we work under the same pressures you do. There's my life cycle. The actual fun answer is farther down in the slides. I was almost going to put it right after this one, but I'll go through the boring stuff before I get to something fun. So this is the life cycle. This is what we see. And early, where before you would see something show up on the external page saying, here's a new aircraft we want to build, we have a request for information, or we have an RFP that says, please solicit your proposal. In there we have a technical requirements document. The neat thing about our world is that I can use these for purposes. That technical requirement document has sections on saying, well, when you show up and you want to propose something to build this aircraft, show me these things so I can make a better decision. You say that you're really good at development. Show me your CMI level certification, or tell me about your development practices, or discuss how you will solve this security problem within the design that you've pitched. So these are neat opportunities for me, I'm thinking. Susan Sal's, where you actually, I think I'd pick you guys, Team A. I think I'll pick Team A. And Team A, okay, if you guys are going to build the design you pitched, then here's what I expect from you. And we work out expectations between each other. Sounds very much like a course I just saw. So the courses you're learning here at Purdue are actually really grounded in real-world activities. Right before we're done developing things, we're designing, we're thinking about what we're going to build. You pitch something in source selection, and I said sounds good, but the practicality is that computing system is now end of life, you're going to use a different model. Okay, that's okay, as long as it has the features I wanted, right? Same amount of memory, same processing speed. Oh, that radio is not available anymore, but the same one that has the same characteristics. Okay, okay. We can agree upon these things. And maybe the design differs because I didn't get all my requirements right. It's really hard to tell you guys ahead of time, here's what I want you to build, but I can't tell you how to build it. I'm not going to tell you exactly what to use. But it needs to be, you know, like this. It's really hard to think ahead of time of all the possible designs you may pitch to me so I can weed out the ones that I don't want. It's very hard to get that right. On the other side of the table, it's very hard to read something that we've written and really understand what we're trying to get from you. We'd like you to build a plane that does this, that, and the other, or put this in a Humvee to do this. Well, I can describe that 10 ways from Sunday, but until we have a conversation, it's really hard. So right before you pass these milestones, there's a PDR, a design review, and there's a critical design document we produce from this. PDR can happen sooner at a certain milestone, but these milestones are very rigid gateways to move from one phase to another, and you can't start cutting code until you've answered these questions first. This is really good stuff. You can complain about government bureaucracy, but this is really good stuff. Now, critical design review is the go, no-go for some of these things, and then we move on. At some point, we're done sort of developing the system, and we actually want to start testing what we've built. And there's a series of tests that we go through, like low-rate production tests or maybe a full operational test. And in there would be security-specific testing where we'd pen test it and red team it, or we'd actually scan it for vulnerabilities using system tools and things, and operations deployment. If you have a life cycle, it should have paces like that. But the neat thing is, today, compared to a year ago, we've got better tools. A year ago, if I asked anyone who's pitching a contract, and I would say this in my contract language, when you write code, I expect you to vet it for code correctness, at least. I don't know if you have logic problems, but please make sure when you write your code, you don't put buffer overflows, you don't do integer overflows. Remember that Ariane rocket? Please don't do that. Casting things right. What else is wrong? Any stack and heap problems. I'll go through a whole list. There's a whole bunch of these flaws, and there's whole categories and a taxonomy I can give. But I'm waving my hand, and what would they do? Okay, that'll cost you $1.5 million, and it'll take me 6 months to have all my guys look through all the source code. It doesn't help. I don't have that kind of time, nor do I want to spend that kind of money. And honestly, if I was on that program and it wasn't written, well, even if it wasn't written in a language I didn't understand, let's pretend I'm not a really good developer. And you know what? Maybe I'm not the right person to interpret the code review results. How do you have someone oversee that to make sure it's just not a crazy activity? It's just said, oh yeah, we looked at them, they're all good. You need someone who actually understands the code. So we have code now. We have code processing tools. We have static analysis tools. We have testing environment tools, things that we didn't have before, which came because, like all good things come, something bad happened and someone said, make sure this never happens again. And you can Google for that. And we now have tools to help the code quality, which means now I can start selecting for language. When I ask people to build stuff for me, I can start specifying the use of tools. Now you can go on the internet right now and pull down find bugs or find flaws or any of these lexical scanners, which is slightly dirty word scanners for code, basically. Hey, there's a lot of false positives. It looks like you might not be checking boundary on this statement that you're calling. And here's a bunch of lists of functions that you really shouldn't be using, and you're using them. It helps, but it's no better than grep. Now, the tools that you can use, and I wish you guys, at least at college level, had access to some of these things. Some of the enterprise level software analysis tools, we're still talking static analysis, are awesome. We actually, at the Air Force, have a Center of Excellence for Application Software Security, the ASACOE. Application Software Assurance Center of Excellence. Everything in the military is a Center of Excellence. Sometimes they're excellent. And these guys are. They've connected with Cigital and with the use of Fortify, SCA tool, the software code analysis. This thing's very powerful. Pull up a whole C or C++ project, and it doesn't just lexically scan the code looking for obvious, maybe code correctness problems. It can find where you're casting an integer and maybe the overflow would occur to you. But it reduces all the false positives because it takes it a step further and actually analyzes the execution path, data paths, data that is taken from external data sources and ends up at a sink without something being done with it. Well, now I have better than a manual code analysis. I can zoom in on a very specific flaw, and it will tell me what the stack looked like that it ran in its head to make it occur. Now, it's not a runtime analysis, but my gosh, that's darn close. So this loop right here, where you have 1024 bytes, and you're counting from 0 to 1023, And the very next line where you put a null at the 1024th byte, you're off by 1. You just slammed a null into someone else's variable. Please don't do that. Wow, that's easy to fix. You took an integer and used it as an unsigned integer everywhere, and then when you compared it as a signed integer. That might be important because 65,536 is less than 10 if it's signed. So we have tools now that we can start asking to use or offering to use for our contractors. But again, remember, I can't really tell them they have to use this tool, but I can suggest here's the level at which you need to do analysis and what deliverables you need to make sure come to us during the course of development so I can be sure that you're doing the right things. And that's possible. And we can offer this tool, or you can use one commensurate. The neat thing is the software industry solving that problem I told you about before. I'm making a case. I'm telling people this code's secure. They're actually working on it. Actually, Purdue's working on it. Mitre and Purdue and a bunch of other folks, a lot of other folks, are working on this problem of making software and security, software assurance and security in general, measurable. It started years ago. Simple things like viruses and vulnerabilities in code. Instead of having one scanner software say, I find 200 flaws, and one say, I found 210, I'm better than him, they double count the same flaw. Why don't we have a taxonomy and enumeration of these things, CVE, and it changed the whole way that works. So with CWE, they have weaknesses enumerations. KPEC is something where we can actually start maybe mapping out how a weakness is exploited. Well, this is perfect for me, because one of the best things for a development crew is if someone can give you feedback. If you're developing something, and you're done with version 1, and I've used it for a year, and you're working on new features, wouldn't you like to hear from me? Hey, that was great, but I wish it did this. Or, wow, this feature's kind of funky. You might want to fix it, because it's not always the right thing. It doesn't always save the right way. This is feedback. Well, we don't often get that kind of feedback loop like we would want all the time. But in my world, there is a feedback organism, an organization. The Intel folks, they know threat data. Here's what bad guys are doing. Well, I'd like to hear that, because I'm building a thing that does this. Are any of these things targets of attack? And if they are, can you tell me something about them? The problem with that is sometimes they can't. I mean, they know it, but they can't tell you. Because if we start building things to mitigate a very, 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 very specific attack, well, then the bad guys know we know about that attack. Maybe that's not always useful. We can't always do that. So that leaves me kind of stuck. But if you could describe the attack in ways that don't give away tactics and techniques, but some measurable way of showing me how weakness is exploited, and if you could tell me what the weakness is in a way that shows me what the weakness in the code is without telling me exactly what the flaw, the vulnerability that's exploited, that I don't want to know how to exploit. I just want to know what's the weakness in my code and how do they get to it, the pathway and the end goal. Well, with these, maybe I can start building those assurance cases. And we're not there everywhere, but at least with CWE, the publishing of the top 25 and the other ones that didn't make the top 25, the top 25 weaknesses people put in code. Oh, this is perfect. I now have a list I can point to and say, make sure you don't put any of these in your code, because they're so obvious and everyone knows them and it's the top one. SQL injection should be gone by now. That's embarrassing. You don't scan your input? That's very easy in some ways. There's libraries that do input validation. Come on, move forward. All right. Oh, I jumped ahead. This is the top 25. So here's the story. There's an Air Force program working with software weaknesses, and just when we needed it, the folks at CWE shared ahead of time, before it was officially published, the top 25 list, which we could then use with our defense contractor, who met us 100% on using tools to improve the software and making sure at least the top 25, because at some point, here's the list of flaws, and here's how many we can fix. Which ones do we fix, right? We should fix the ones that remotely exploitable. Okay, that's good. Ones that definitely smash a stack, like a heap overflow might be slightly less risky than a stack overflow. And if it's not in the top 25, well, that's what we did. And right now we're exploring how do we get this better? How do we move this along another path? So we're still keeping our eyes on. This is where something like an effort of changing the context of the security problem is important. I live in a world where most people go, it's really nice that you guys are trying to a taxonomy or an ontology, and I don't know the difference, and why would I care? And you're trying to enumerate flaws. Okay, whatever. I've got this stuff to build, and I need to make it better. you didn't tell me how your stuff is going to help me. So come back when you have a tool or something. Well, no, this is a direct example how something that's trying to change the context of the security situation for software could be used in a way directly, with or without tools, to maybe specify something that we're talking the same language. These are 25 things I don't want to see happen in my code. There are lots of guidance from the folks I work with, folks outside, working groups trying to figure out how do you apply these sort of things. And I've read and distilled some of these, so I'm trying to quickly move down to the place where I can tell you what I'm doing. Here's a nice scary report. Actually, Mitre was part of this, and it's the mission impact on foreign influence on DoD software. It overly focuses on foreign influence, but the tactics, the things you can do to make sure your code is better, using static analysis tools, making sure you secure them when you have a repository and putting them away, making sure that you track all changes and additions to code with some kind of authentication that will withstand scrutiny. These are good practices. There's been developer guidance around forever. There's like Google anywhere. You'll find a list of, please don't use these things when you're doing C and C++. Here are good things to do. There's tons of coding sites. But anyway, there are things that we can actually point to. Documented guidance for writing code. And the DHS, the Department of Homeland Security, has spent a lot of time on this because they care very much about this. And these guys are starting to act as an aggregation point. And you read any one of these practices here, whether you do some architectural threat modeling. So when I'm building this thing, what's it going to face? That would be nice to know when you're designing it. When I'm actually writing the code, is there something like coding practices, coding rules, code analysis, like the static code analysis, or maybe other kind of analysis tools I can use to make sure that in my build process, when I shoot my code in each night, the shame list comes out and who broke the build? Run that code then. Or run it every week on a build or an external build. Is there any other test tools I can use? Can you do something to the system to see if... So these are very good processes, and they're very agnostic. They're not telling you how to do them. And they set up a site to aggregate all this with exact how to use them. So you've got, here's kind of the goals, and here's kind of the ways to get there. This is a cheat sheet for doing good software assurance. If you take these couple pieces that I put in these last bunch of slides, here's the boring part. Ironically, and I do love the ISO standards. There's an ISO standard for doing this. And it has ISO standards framing up how to actually execute those steps that are suggested by the other folks. And I know it sounds boring, but read an ISO standard ones. These things are actually very good. We were using in the financial industry ISO standards and the British standards before that for information security because here are 10 domains to worry about and here are the kind of controls you need to make sure you answer for yourself if you want to be secure. It's a cheat sheet. And it might not be perfect. Like the controls we work with in the Air Force. They're not perfect. There are 132, 133 controls that say you have to do these security things. Not perfect, but they are a list. And they do have a spirit and intent that actually solves a problem. And if you do knock them down, that's better than not having a list. It's better than not doing those things. So here's what I thought I'd do. Take those things early. Apply them at these places. Put design improvements in. This is my build-up slide. I'm going to get quickly to the end because we're right out of time. Okay. There's my summary. So all those pieces I sort of rambled on about all do come together in what I'm doing. I'm trying to leverage template language or ask for things I know I want to see. I want to see static code analysis used. Well, how do I ask for that? How do I specify when you build something is good enough? A measure. Because if you say it needs to be done a certain way and there's no measure to do it, it doesn't happen. The things we are missing are feedback loops, like I said. And we're trying to figure that out now. And we're still looking for those metrics and measures from the industry. Thank you.
Any questions?
Any questions? Was that boring?
I have one. Actually, it's an interesting. I was just thinking of a completely different domain. I'm involved in aviation, and the checklist, which every pilot runs through before you start your plane. It's like a religion. You do this, but
and you may not agree with all of them all the time.
But if you look at aviation, like at Air Force data on fatalities, aviation accidents, the introduction of the checklist is the single biggest drop.
Yeah.
And to what extent do these ISO standards or some of these others provide that level of, I mean,
So
could they be used
the United
almost
States
at that level?
The United States is different than Europe, right? Speaking from like a financial services perspective, the way that security or attestation works in the United States is, I want to do business with you. I want to exchange financial data because you're a bank and I'm a mutual fund company or something. Well, okay. Well, I worry about him and he worries about me. So we hire auditors. Third parties come and look and they make an attestation. Yeah, trust my name, PricewaterhouseCoopers or whatever you want to pick a name. And I looked at his data center and his computer controls and his general controls on handling money, and he's good. He meets standards. Well, he does that to me and everyone. So they have these few very well-known ones. So attestation is the way it's done. They take a third party that makes a statement about it and backs it up with, money and sort of like risk management for like an insurance company would do, shift the risk to a third party. In Europe, it's very different. They look to standards-based and conformance to a standard. That's why the ISO standards generally impact Europe and Britain much more than they do us. But the sad thing is even if those aren't being held for us to be compliant with, they do solve a lot of problems. And I see smart places using them in the United States. I don't see them enforced in any way, though.
Any other questions? I'd like to thank you.
Thank you.